Hi everyone, welcome back to the next lesson. I hope you enjoyed the lessons so far. And I don't know if you remember the question last time, but it was to think about how we could take the strategies that we've used for 2D circles, right? A circle going to rings, slices, and boards. How can we take that and put them into 3D? Well, here's a few ideas. The key concept here is that we're actually taking similar approaches, but we're sort of spinning them or rotating them to sweep out the 3D version. So, we can take a circle and imagine it as a sphere. That works. Or we can take a bunch of rings and imagine kind of spinning them like a coin to form a series of shells. It's the same idea where you have these sort of onion layers happening, but now it's just in 3D. So we have these kind of really thin shells wrapped on top of each other. Slices become wedges. I can imagine sort of instead of cutting a pizza, you're sort of cutting an orange. And another way to think about the wedges also is that you're sort of pushing up some Play-Doh through a mold, and maybe the size of the mold is changing as you go along, but you're sort of extruding out this shape, so you have that kind of triangular section being formed. And lastly, our boards become plates. And so what's interesting here is boards kind of looked complicated in 2D because it's sort of really robotic and it seems a lot more complex, this up and down pattern compared to the other two. But plates actually look pretty simple in 3D. You can imagine a stack of pancakes or maybe some barbells or something where you sort of have a small disc and it grows and it shrinks again. So what's neat is that certain strategies that might look complicated in one domain are actually not a bad idea in others. So the key concept here is that we can take this idea of step-by-step thinking and apply it pretty much to any shape here. And one neat idea, an application that's just actually happening in modern times is 3D printing, where with 3D printers, you sort of have this constraint where you might be building up things layer by layer. And in that case, you probably have to go with the plate strategy. Maybe the wedge, if you can sort of, layer it down and build it along kind of that vertical path. But oftentimes, maybe a plate strategy would be the simplest way. So again, the concept here is to kind of get you thinking and to look at a shape and be able to, just dissect it and say, okay, we have a few different strategies. Is there an advantage to one? Why would we use one or the other? And maybe in different domains, we prefer a certain strategy. So with that, we can actually come back to our original question here. So, in the beginning, we showed these equations, and we intuitively knew that they were just kind of related. And we saw how the first two were related in the first two lessons, where we saw making the ring triangle and separating it out. And now we might have an idea how all of them are related. Let's take a look. So right here is sort of a summary of how we might be able to jump between the different versions. As you see, we started off with a circumference. We sort of time-lapsed it up into an area. We got it filled in. And now that area, well, that is a pretty good candidate to build up a sphere using these kind of plates. So we sort of thicken it up a little bit, and we time-lapse that. So this is kind of a double time-lapse, right? We had the first one make the area. The second one makes the volume. And now we have a sphere that was sort of built up by these plates. And lastly, if you want to get back to surface area, well, we can sort of take that volume, that sphere, and sort of get one little onion slice of it. So we sort of x-ray it just a little bit and take out that outer little shell. And now we've got our surface area. So at least intuitively, and now we have a pretty good metaphor for how we would describe the process of going from one of these equations into the other. So going from 2 pi r all the way to 4 pi r squared. Now, one thing you might be noticing, though, is it's getting a little bit difficult to actually describe our ideas, right? I'm looking for analogies, rings, plates, time lapses, x-rays, shells, onions. I'm sort of reaching to find ways to describe it because we're trying to visualize everything. Visualization is a helpful technique to understand a concept, but eventually it'll break down. If we're trying to talk about fifth dimensional objects, I can talk about it, but I can't quite visualize it. So in the same way with calculus, we want to kind of come up with a vocabulary and symbols so we can talk about ideas that are actually probably difficult to visualize directly. And what's kind of interesting is we sort of went through this process with numbers. When we started off with numbers, we had the unary counting system, which is kind of what we use when scoring a game, where you have 1, 2, 3, 4, 5 with a line. We sort of use that when it's really quick. But what's happening, though, is that each number is actually a literal representation of the idea, right? So 1 is 1 line, 2 is 2 lines, 3 is 3 lines. And writing down 3 is 3 times as much work as writing down 1. And writing down 1,000,000, well, you're never going to do that because you're trying to represent a million with basically a million lines, in the sand. The benefit of symbols is that we can actually make these shortcuts, which are much easier to read and much easier to write. So, it is a lot better to write 2 plus 3 equals 5 than trying to even write it out in English. 2 added to 3 is equal to 5. It's sort of really cumbersome to try to make a direct translation. At some point, it becomes better to have these little shortcut symbols and use those instead. Another advantage of that is we're sort of I'm anthropomorphizing math, but I'm letting math do the work for me. So when we write decimals in this way, I'm sort of letting the math keep track of how many actual lines in the sand there are. I say, okay, 2 lines of sand, 2 lines, 3 lines, 5 lines. I'm not having to think exactly how many there are or even imagine them. I'm just sort of giving it commands, and the math rules are sort of crunching through and giving me the result. And so the advantage of calculus is that once we sharpen it up a little bit, we can tell calculus to do these transitions without having to actually visualize everything. I mean, we probably want to understand that there's an area turning into a volume and maybe it's a plate, but we don't really need to think about how to chop it up. We don't have to worry about unrolling the triangle, actually unrolling it and measuring it. We kind of let the rules of math do a lot of that work for us. So it's kind of a neat transition where you stop having to visualize. Visualization is awesome and I love it, and we need it as an introduction, but we don't want to require it for every problem because, well, at some point our brains, we can only handle so many dimensions. So there's sort of that interplay a little bit. So in the following lessons, we're going to talk about the language of math and how we're sort of taking our intuitions and turning them into kind of descriptive words and symbols, which will actually simplify things for us down the road. So take these lessons, at a high level. If you're interested in just the kind of the analogies and the descriptions, watch the videos and sort of poke through. But if you're interested in performance, then go through the article and kind of, make note of some of the symbols and how they're being used. Happy math.